Thank you, Rajesh. So what I will talk to you about is to generate complicated flows, chaotic flows in systems which are very highly viscous. The number that you see of order of 1 Pascal second viscosity is roughly of the order of that you see in honey. Honey is a few times more than that. The length scales that you'll be in, I'll talk to you about in these experiments are of the order of 100 micrometers, which means that the system is of very low Reynolds number. This is not a pressure-driven flow, so essentially the average velocity in that sense is going to be 0. So what I'll do is there are a few things which this talk will cover. One, it will range from generating chaotic flows to suppressing these chaotic flows and then extract something useful out of it. Chaotic flows themselves also could be useful. So let me give a word of thanks to all the people who worked on this problem. This is Atul Vashne, who was a PhD student with me, Smita Gohil, Mayur Sathe, Shobha Bhattacharya, Anand, and J.B. Joshi. So let's start with something which is simple. And the idea is that if you have an object which is, say, of charge Q immersed in some fluid, you apply a force to it, and the force will depend, you apply an electric field, and the force will depend upon the charge that's there on the object, and this object is going to move with a velocity which depends upon the viscosity of the fluid. Now, all objects don't have charges, but if you put most solids into liquids and in aqueous medium, a solid surface usually has a charge. Though overall the charge neutrality is maintained, this object will actually move under the influence of that charge and the electric field. These are known as induced charged electrokinetic phenomena, and the idea is this, that if you have, for example, a charge like this, and for example, you have an electric field up there, you have an object on which, say, you have, because there's some polarizability of your diffuse layer up here, there's a minus charges on one side, there's a plus charges on the other side, there's an induced dipole moment in the system, and if the dipole moment is exactly aligned opposite to that of the electric field, you will have, or in the direction of the electric field, either way around, you will have a torque in the system which is going to be 0, but that's an unstable equilibrium. If you slightly tweak this whole system, you make an angle between the mu and the E, the torque is finite and this object is going to rotate. And the idea is that it's going to rotate in a direction which is going to be perpendicular to the direction of the applied electric field. So basically, if you have applied electric field, this object is going to roll. A phenomena which was actually discovered quite long ago, and it's called as a Quincke rotation. And it depends upon few things. It depends upon what the conductivity ratios are going to be, what is the dielectric constant ratios in the system, the charge relaxation time. So if you have a conducting fluid and if you place an electric field, there is a time scale over which the charge is equilibrated in the system. That's your charge relaxation time in the system. And if the system crosses a critical threshold field, if your field is larger than a critical value which is given by EC, you'll have a rotation in the system. And if you have noticed there that this is the electric field, that's your dipole moment in the system, and the object usually rolls in this direction. And this Quincke rotation has been put to good use by many people. There's a beautiful experiment which this is from some group in Oliver Duchot was a part of it. And this is the initial movie that you see up here is basically you have an electric field which is out of plane. So this is an electric field which is going out of the plane here. You apply electric, the field is above a particular critical threshold, and you can see this object actually start to roll. If you cross a particular density in the system, then you start getting very nice waves, and these are rollers which actually start to move. They coordinate themselves, and then you have a wave which moves only in one direction. Now, this is one version of it. There have been others who have worked with this particular Quincke rotation and variants of this Quincke rotations to get interesting systems. But most of these experiments have been done on aqueous systems. The particles are solid particles, and that's where my talk will differ. I'm not going to use solid particles. Instead, I'm going to go to liquid drops. And why are liquid drops different? Well, the liquid drops, first of all, don't usually have a large interfacial charge unless you're putting them into a surfactant solution. And if it's an oil and oil, you don't expect it to have large interfacial charges. More or less, a liquid drop, the number density is not kept constant. You can have liquid drops which will deform under the application of an electric field. You can break a liquid drop and things like that. So essentially, liquid drops are going to be very different than that of solid particles. Now, if you had a dielectric liquid drop placed in an electric field, for example, here, that you have the electric field is in this direction, and you apply a you place a dielectric object up here. The Maxwell stress is going to be normal to the surfaces, which is going to cause this object to actually elongate. And so you always have a dielectric object put in a liquid drop, another dielectric medium, if you apply an electric field. Tangential stress, the normal stresses on the system is going to make the object prolate. And you can find out the eccentricity of this object. It's a simple calculation. And that's the eccentricity of the object. If you wanted to have an order of magnitude estimate of what the critical value of this is going to be before this object is going to split open, the equilibrium size is basically a balance between the capillary pressure and the electrostatic stress acting on the object. For E is equal to 1, you think this is going to be a very slender object, and such an object is going to break down, and you can have an order of magnitude calculation for E star, and it works quite well if you put the diameter of the particles, that liquid drops, that you can actually work around with. Now, typically that's a system which works on for a dielectric object in a dielectric medium, but if you did something different, which most things are not perfectly dielectric, so you have some charges in the system. And this was a variant of the problem which was done by Taylor and way back in 1969, and it's been still worked on because certain aspects of this problem has not yet been done. And the problem is this, that you immerse a perfectly insulating object, assumed to be perfectly insulating object, which is the region B marked here, inside a liquid, which is the region A up here. And this outside liquid is poorly conducting. Means it's not insulating. It has certain amount of conductivity, but the conductivity is not going to be large. So what you do is you induce currents in the system as you apply the electric field. This currents, because this is a conductor, poor conductor, it deposits some surface charges at the interface. There is tangential as well as normal stresses acting on the system. The flow generates the tangential stresses. And if you have tangential stresses on a drop, the only way to balance this tangential stress is to set up flow fields in the system. So you generate flow fields in the system, and that's how the drop attains an equilibrium shape. And that's typically what you have in your system. You can write your Navier-Stokes equation, forget about the advective term up here. The first term is the pressure term, the second term is the shear stress term, and the last one is the body force term, which comes from the electric field. You rewrite it in this particular form. That's your stress tensor, which comes from the Maxwell stress tensor. This is your shear stress tensor, comes from the viscosity of the fluid. If you solve for this problem as Taylor had done, what you get is the flow fields up here. So this is the flow field that you have. Internally, there are this four parts. The flow fields breaks down. There are circulatory flow fields up here. And this drop actually attains an equilibrium shape. And this shape depends upon a few things. One, the destabilizing effect is from the stress that comes from the Maxwell's stress, which is epsilon naught square E squared term. The restoring term comes from your surface tension. So you describe something which is known as the capillary number, which is a ratio of the stress, the stabilizing stress, and the restoring term, which is the surface tension term. And in response to this, basically the drop deforms. So you see, in the earlier case, I had only drawn a prolate object, but this I have drawn a oblate object, which means that the drop can actually become oblate. And this ratio is called as a Taylor's deformation parameter D, which is given by L minus B by L plus B. And the whole idea is to find out what is this D as a function of the capillary number. So you change the electric field up here, you change epsilon naught, epsilon R. Epsilon naught you can't change, epsilon R, epsilon you can change. And if you do all of that, and if you change the conductivity ratios in the system, then you basically can change what this value of D is going to be. So just for the sake of completeness, that this expression of D has something which has a phi up here. And the phi is a ratio of the electrical conductivities, which is a function of R. which is sigma in by sigma external. When I write in, it means that the inner fluid, that is something up here. The external is the outer fluid up here. S is a measure of the ratio of the dielectric constants, and M is the viscosity ratio. So here is this problem. So instead of doing one drop in the system, which Taylor and many others have done, I'm going to put many drops in the system. And let's see what is the problem with such a system. First thing is this: the injection is via. So you have two plates like this. I'm going to put a lot of these drops up here. I'm going to see what's going to happen. As you apply an electric field, because this phase, which is a continuous phase, is conducting, weakly conducting, but conducting nevertheless, there is going to be a current which is going to flow in this circuit. Now, unlike electronic system, where basically the atoms don't move and only the electrons can move, in liquids, when ionic conductivity happens, you basically have the ions which are going to move. If the ions move, they set up an electrohydrodynamic flows in the system. This is basically because of this term that they generate. They change the stresses on the system, so they set up flow fields here. These objects move in response to that, and then make this whole thing very complex. So we'll look at the complexity in the system in a short while. So the experimental scenario would be like this. I would have taken 2 indium tin oxide plates so that I can see them. I'll plate a spacer up there. Silicon oil is basically my perfectly dielectric system. Not perfectly, but anyway, it's a better dielectric than my immersion oil. Immersion oil or a castor oil that you can use outside an oil. I place a field which could be DC or AC, and I'll mention it to you. And these are your ratios of your systems. You can see that the conductivity of your immersion oil is 4.6, which is greater than that of the silicon oil, which is inside. So that's the system. So this is the light blue part is a more conducting part. What you see is the dispersed phase, or the spots that you will see inside will basically be parts which are less than that. So this is what is going to happen. So what I'm going to show you is one drop. This is the applied electric field. The applied electric field is going out of plane. You're looking into the cell. And if you are above a particular threshold field, this is what you see. You will basically see this drop moving, which is almost like the Quincke rotation. But it also generates very large scale flows in the system. Now, instead of having one drop, the field is DC now. You could start now with many drops, and this is what you get to see. You get to see a very turbulent mixture. And look at this. This is a very highly viscous system in a very confined geometry. If I stop this flow, immediately things will stop within milliseconds. So what do you have here? You have multiple things. One, you have, let me just play the movie again so that I can make my point clear. You start off with the drops which are larger. So as soon as I apply the electric field which is above a particular value, the droplets break, they coalesce, they set up complicated flow fields. And our purpose would be to understand these complicated flow fields and find out what the energy spectrum of these flow fields are going to be like. So if you look into the flow fields, there's something very interesting. Is this flow field is not actually homogeneous. You can find structures like this. I don't know whether it will appear to you. These are almost like the Rayleigh-Benard convection cells. You can actually have little small cells in the system. This is more clearer in this particular movie, which you see that the space itself is not, so these are like small tracer particles, and you can see that the tracer particles everywhere in the system you don't have flow. You have certain flows which are localized at certain places. So these are the places which basically you have large flows. And so you inject the system energy from the boundaries. This energy is basically get localized in certain vortices like this, which keeps on rotating up there. And via these vortices, you have an energy transfer which goes into or a momentum transfer which goes into the continuous phase. And so what you do is, just to look at this phenomena, what I have done is I've put a red dye up here. This is a very viscous system. It would have taken you like months for the diffusion to take place. And I'm going to put on the electric field. And because there are these active processes in the system, you see diffusion in the system. And the diffusion not only occurs, so you can see these large vortices which are basically carrying this fluid, the red fluid from bottom to the top. And I'll characterize it later. So that's what we say is there's a multi-scale about it, because there's one scale up here, the other scale which is the injection of the current which is homogeneous all over the place, and things like this. So So you can look at these structures, which is basically to say that, if I am at a small electric field, I can get these lines, which is remainder of the Rayleigh-Benard convective cells. If I increase the field, the cell spacing doesn't change. They roughly remain the same, but it becomes more space filling. And if I still go up in the electric field, it becomes still more space filling. So you basically have more efficient mixing, but the cell structure doesn't change as I change my electric field. So what you can characterize is, you can do something like this, that you do the same experiment but at different fields. The left-hand experiment is for about a volt per micrometer. The right-hand is for about 5 volts per micrometer. And if you look at the front, the way the front moves, it gives you an effective diffusion constant like phenomena, which is almost like square root of T, which tells you that this is like an effective diffusivity in the system. And the diffusion goes like, for some small values, the diffusion is small, below 3 volts per micrometer. And I'll tell you what's so great about this 3 volts per micrometer. And suddenly, as you cross the 3 volts per micrometer, mixing becomes very efficient. And just if you wanted to know the molecular diffusivity, it's a few orders of magnitude smaller. It's about 10 to the power minus 6 millimeters squared per second. Whereas these numbers are about 10 to the power minus 3. This is about 3 orders of magnitude smaller than what you'd get just from molecular diffusion or thermal diffusion processes. So here are the 3 phenomena that you see. You see droplet motions, you see breakup, and you see coalescence. Now, before I go into the energy dispersion relationship, which is interesting, a standard look into the Kolmogorov's picture, which is something that we grew up with, is that, especially it is true for a pipe flow. You inject energy at the largest length scale in the system, and then there's an inertial cascade. And if there is an inertial cascade, then this structure actually breaks down into smaller and smaller structures. Still, you hit the microscale with the Taylor microscale up here, and then the dissipation takes part. And if there is an inertial scale in your system, if you have an inertial scale, then Kolmogorov came up with this argument where EK goes like some energy pumping efficiency, that how much energy do you pump into the system or dissipate out of the system per unit mass, and the wave vector goes like k to the power minus 5 by 3. Now, this being a multiple energy scale system looks like more different from that of a Kolmogorov scale, because in a Kolmogorov thing, you just have energy injection at one particular scale. On the other hand, there is the standard Rayleigh-Benard convective cells, where you have energy injection at different length scale, because as you have a Rayleigh-Benard cells, a Rayleigh-Benard convective cells would be something which is, you have a low temperature, you have a high low density up here. That means you have a high temperature up here. You have a low temperature. You have a high temperature up here. So basically, what you do, you have a high density up here, and you have a low density up here, and of the fluid. And if you have such a system, then basically the fluid will start to go up and then come down. Yeah, this is right. So you start having convective cells, and if you basically reach to a perfect parameter, then you will basically have nice convective cells here. And the problem with this, and the difference in this and a pipe flow, is this: in a pipe flow, your pressure term is the only term that you have, whereas in this one, this is a buoyancy-driven system, and in a buoyancy-driven system, the forcing term will come from your alpha times some gradient of some temperature up here, because that's the density difference that you have here. And so the forcing term will depend upon the local temperature in the system. So that's an additional term that you have. So you don't inject energy only at this scale, but you inject energy over a large scale, which is, say, up to kb, and then you have the inertial scale from which you have down. So basically what happens is, as the liquid goes up, it gains potential energy, loses kinetic energy, so you expect the drop to be larger, faster than that of the Kolmogorov scale. So if this Kolmogorov scale is of the order of k to the power minus 5 by 3, I think this would be of k to the power minus 11 by 3. Maybe this number is wrong. Anyway, so it's faster than this particular scale. So you have, at least in Rayleigh-Benard scale, you have energy injection not only at at one scale, but you have over a particular values of scale where you can have this energy injection. Now, this is a trivial way of looking at this whole system. What do I have is, if you were to do an experimentalist version of this whole argument, you have, say you're doing an experiment in a wind tunnel. That's your grid, which is basically injecting some length scale. Instead of putting one grid up there, you keep on putting multiple grids in front of it. So this would be what would be something which is equivalent to an energy injection at multiple scales, because every particular grid that you put and the wavelength corresponding to that grid tells you the length scale at which you are injecting the energy. So you basically suck out various energies by putting grids at different length scales in the system. So what you do is and this is with a pinch of salt that you have to take it. This is not a nice PIV because this is a two-phase system. PIVs are meant to be done for point sources, but I can show you the cross checks of it, and it kind of goes through. If you did a PIV in this particular system, you'd get an energy dispersion which roughly goes by 1.4. So that's the energy dispersion you have. And also better data up here because this is not a large scale over which you plot the energy dispersion relationship. So here is this energy transfer that you have in a system. You have a battery up here or a source, which is a current. And the current is driving this whole system. These things move. So you basically dissipate energy in two ways. Either you heat up the whole system, which you probably is radiating and goes into the system, goes into the atmosphere, or there is shear stress which is pumped up, which actually is exerted at the boundaries. So to measure both of them, what we do is you measure the current fluctuation that comes up from your cell. So you put a cell inside a rheometer. You measure carefully what is the power that is being injected into the electrical power that is injected into the circuit. And you also keep track of what are the shear stresses that are acting on the plate. So if you look at this, then you see that this is a critical value beyond which the flow starts to become turbulent. And suddenly there is a large injection of energy into the system. So basically the power suddenly goes up. So if you look at the power, your power would be like I square R. So suddenly the system is basically drawing more current than it would have otherwise done. So it's not like an ohmic resistance that you have where then your power would go in a monotonic way. It's also monotonic, but not in a sudden way. It changes about this value of 3. If you did the same experiment, but now tried to measure the stress that's being exerted at the surface of your or a plate that's attached to a rheometer, you can measure the boundary stresses of it. And you can see up here is if you are at a low enough stress values, the rheometer hardly measures something, and then suddenly it starts to measure a lot of signal. This up is exactly at the same point at which the system also starts to draw a lot of current. Now, a problem with this measurement is that you cannot measure anything which is at small time scales, because you're basically averaging out all small scale events. You're only going to take events which is at the scale of this particular sample, which is pretty large, of the order of about an inch. That's about an inch. So anything which is smaller than that, those kind of fluctuations you won't see because they would get averaged out. But nevertheless, if you went and plotted your system, then this is what you'd get. You'd again get, so I showed you from PIV that you got something which is close to about 1.4. If you measure this power spectrum from the stress fluctuations that you have as measured by the rheometer plate, then also you get something which is about 1.4. This is slightly better because you have 1, 2, 3, 4, 5 orders in one side and 1, 2, 3, 4, 5 decades in the other, 4 decades in the other side. You can trust this. Anyway, we have not plotted the frequency which is beyond this because those high frequency data are not trustworthy because they're averaged out by the size of the rheometer and the inertia of the rheometer. To do something better, what we did was we inserted a small cantilever. This is a small cantilever that an optical fiber, which is like a cantilever which goes into the system, and then looked at the fluctuations of the cantilever. Now, this is an overdamped system. The cantilever is long so that it does not have any resonance in the ranges that we were actually looking for. And then that's the power spectrum that you get from the cantilever, micro cantilever. You can see that below 1 Hz, which is basically you have 1.4, which comes over here. And then crossing 1 Hz, you basically have something which goes like 2. So So this goes like -2 slope. And there's a knee up here. If you have used a cantilever, then the first doubt that somebody gets in his mind is, well, you know, it's a cantilever, is like, has a response function which is like a Lorentzian, so -2 is probably just a response from that. But the noise level of the cantilever is somewhere here. So basically, if you just look at thermal noise of the cantilever, it would just be up here. This is actually signal that's coming from the fluctuations in the system. Okay. Well, we were not the first people who actually did it. Probably we were the first, but anyway, there were others who had also done it. And the idea there was that you could actually do this by having the contrast in your conductivity. And so what they did was they did water, which is about 1,000 times lower viscosity than what we were doing. So they mixed two channels at the same temperature of the same liquid, but one having more ionic concentration than the other. So basically what you have a jump in the conductivity up here. So that's a low conductivity system. This is a high conductivity system. If you apply frequency in the system, if you apply about 8 volts and 20 volts, so this is peak to peak, and this is done in an experiment which is roughly about 100 kilohertz, then you can get mixing in this kind of system. Remember that in this particular system, there is no second phase in the system. So for example, in my system, what I'd shown you was that this is one liquid, that's other liquid. They're kind of macroscopically phase separated. What we had was a microscopically mixed up state of bubbles of one kind into the other phase. So this was the connection that I was trying to draw up with, that if you have a Rayleigh-Benard convection, then what you have is you have a forcing term which depends upon the height. As the liquid goes up, it basically gains a potential energy, and that has a cost to the kinetic energy. So that's one driving term. And the turbulence, and it depends upon the local temperature. So it just depends upon the scalar variable temperature up here. On the other hand, the electric field case, it depends upon so if you look at this particular expression, it depends upon basically the gradient of your conductivity. So it depends slightly differently than that of the Rayleigh-Benard convection. So this could be the electrokinetic turbulence, which is in many ways different than any other turbulence that we know of. So that's 11 by 5. So you have an energy. So this is the Kolmogorov scale. That's the scale at which you inject energy. The energy goes down all the way up to the Taylor scale, and then the kinetic energy is converted into heat, and it's lost. And if there is an inertial scale up there, then the scale goes, and then you get k to the power minus 5 by 3. If you have the Rayleigh-Benard type of convection, which is buoyancy-driven convective flows in your system, or stratified flows, stratified atmospheric turbulence in your system, then you can have energy injection up to this whole scale of LB, and again, what this LB is. But there is multiple scales over which you get the energy injection in. And then it's expected that it's not really seen well in the Rayleigh-Benard sense, but probably in the Rayleigh-Taylor experiments, one sees that in this particular scale, you can have EK, which goes like k to the power minus 5 by 11 by 5, which is faster than the Kolmogorov scale. On the other hand, what you have here is you have an energy injection over a multiple length scales, and I don't even know whether this length scale, right, it goes up to here or not. If there is an inertial scale, and if these scales are inertial at all, I don't even know whether they are inertial scales or not. There is a scaling which goes like minus 1 by 4 to a particular point, and then crosses over to become minus 2. So in this way, this is a very different turbulence than any other turbulence that usually is talked about. But multiple scale energy injection is not so uncommon because that's a very efficient way of getting mixing in the system. So if you want to mix systems, it's not ideally that you mix it at just one length scale. You mix it at multiple length scales. This is where, if you look at the stirrers will almost show you that there are multiple length scales, and there's a lot of design which goes into the stirrers mechanism, which makes energy transfer much efficient, and if you have multiple scale energy injection in the system. Now, what happens is this is all strongly hydrodynamic dominated system, but what happens if I start putting a frequency term to it? So what will happen is, instead of having this is my stress tensor, so instead of having just a steady part of it, this will have a time dependent part of it. And so will my deformation. Deformation will have a steady part of it and a time dependent part of it. Yes, the steady part will also depend upon what frequency you are doing, because it depends upon your dielectric constants and conductivities, and all of those parameters are a function of your frequency that you have in your system. but the time dependent part, this is the tangential time dependent part, and that's this is the radial time dependent part. I think. Okay, yeah, this is the radial time dependent part, and that's the tangential time dependent part of the system. And what you get is that this one depends upon 1 by omega square. So if you go up higher in frequency, you basically lose on your time dependent part. So basically things become more and more sluggish. So this is what would happen if you are doing your experiment at 1 Hertz. Then you can see that this is dominated by a lot of coalescence and breakups and things like that. The middle panel shows you something which is at about 2 Hertz where droplets are not doing much. And the third panel basically shows you 3 Hertz. By that 3 Hertz, the droplets are basically all the hydrodynamic interactions almost got killed up. So if you looked at how circular the droplets were in the image, the spherical droplets, but you're seeing in an image, so it's circular. So basically these are very non-circular droplets. You get lots of elongated droplets up here. But as you move down, as you move up in frequency, this becomes sharper, which basically tells you this is a metric that we have hooked up. Basically tells you that for a circle, the sky is going to be 1, and things are basically circular up at higher frequencies. But then something takes over. Once you have killed up your hydrodynamics, you have dipolar interactions in your system, and then you start getting coalescence. And now, the reason coalescence is also very important in practical world is because many times what you have is when you get your petroleum product, for example, you have about a 30% content of water in it. Petroleum is pretty heavy. If you want to extract that water out of it, then one of the good ways of doing it is to apply an electric field, because electric field then induces coalescence in the system. You start getting bigger water drops, and then you can decant it out of the system. So here is this problem that you have dipolar interactions in this problem. So basically what it tells you that if the dipoles are going to move in this direction, there's going to be an attraction. There's one time scale which is given by the viscosity of the fluid, so you know how fast they can approach it. Once it has approached it, then there is a problem of lubrication fluid, so the fluid has to go out, and then the two fluids will actually have to merge together. So if you do this experiment, this is all under the assumption that there is no charge on these systems. But let's just look at one particular thing which we found to be odd. Is say, for example, what you do is you apply an electric field to this system. I said that priori that you assume that there is no net charge on the droplets. And then you are applying a very small frequency to those droplets. First thing that you see is the droplets to move out of plane and in plane into the system. So once the droplet goes out of plane and then it goes into plane. You realize that if it has to do that, then the droplet must be changing its sign of the charge that it has on itself. Because only a charged object can move in a direction in an electric field. So its QE will be the force on it. So when E changes its direction, then suddenly the droplet actually starts to move in the other direction. So it goes up, then it does something, then again comes down. So it just tells you that the droplets are not neutral. They basically have some charges on it, and it responds to those charges. So what happens is if you start putting these droplets and quench it at a high frequency, what you see is you get basically these things. So you have two layers, which is almost like frustrations that you can get in confined colloids. You get one droplet layer, which is at the bottom plane, and then you have got the other droplet layer, which is the other plane, and they form some interesting labyrinth patterns up here. Unfortunately, these patterns are not very stable, and these patterns will actually coalesce in time. So what you'll have here is as these droplets move, they start to coalesce and become larger and larger droplets. This is a 25 Hertz. You cannot do much better, even if you go to 1 kilohertz, where you think that you have actually killed all hydrodynamic interactions. But you can see that this droplet is at a different plane. It's basically basically annihilating all the droplets that's in other plane. So all of these droplets will come, and these droplets starts to glow, so that's no use. You basically can't create an array of droplets. However, if you play around with your density that you have in your system, and you prevent the second layer from happening, then you can basically generate something which is like this. It's a nice layer of droplets. And what you do with it is that you look back to the second part of the steady part of your equation, which tells you that you have a deformation parameter which depends upon the electric field square. That's fair enough. But it also depends upon this S and R, and which depends, and S and R is a function of your frequency. So what you do is so that's a typical example that I'm doing it at a particular frequency, and you can see the droplets constantly deform. And this deformation could be prolate or oblate. This particular picture shows this deformation is basically oblate field. So when the field is maximum, then basically the droplet is almost squatting. So that's not what typically a dielectric droplet would do. So what you do is you basically sweep in frequency. So if you go from about 70 hertz to 1 kilohertz, you can convert a droplet which is basically circular to something which is prolate, and basically this is oblate. It's oblate to prolate transitions. And if you're enterprising, you're basically going to put all of that and then use it as a lens array. So what I'm plotting here is basically I'm plotting the d parallel and the d perpendicular, which basically measures the deformation of the droplet. So you can see the droplet up here. You change the frequency in the system, then the d parameter basically changes. So for a prolate, it's about 1 kilohertz. So I'm going to change my electric field so I can make something more and more prolate, because the E square term goes up. If I am at an oblate at 20 hertz, I can basically change my frequency and make it more and more oblate. So basically, if these droplets were to act like lenses, I can basically now change the focal length of this lens by applying either changing the frequency or applying larger and larger electric fields. So to prevent coalescence from happening, this is the trick that we use. We basically put in a disorder on the surface by selectively etching out parts on my ITO cover slip. And so this is at a 3 hertz, which is, this particular system is still turbulent. You go to 8 hertz, and then suddenly you have this droplet array that you can have. It's basically set up on the system. You can take this system, so you basically will have this nice droplets up here. You can see a little bit of dynamics still going on up there, because hydrodynamics is not yet killed at about 8 hertz. The corner, there's some flow up here. And so you put it on a grid, you change your field across. You can basically change your focal length. This is basically micrometers. You can see the numerical aperture is not bad for system, is 0.2. And you can change your focal length from about 120 micrometer to roughly about 80, 90 micrometers. And this is basically the quality, which is pretty high, which tells you this is basically the difference between your bright and the dark spots in your images. So the way we do is we place a grid up here, and then observe this grid through this droplet array, and then go up and change the frequency in the system. So you can see this is out of focus. The first image is out of focus, and as you are sweeping the frequency, it basically comes into focus. So that's the story about how you can use multiscale flows. You can quench multiscale flows, and then get interesting physics out of it. Thank you.
Questions?
So you seem to have both coalescence and splitting of drops as well as Quincke rotation, right? There are 3 different things that are going on, as I understand, in your experiments. So all the exponents that you get, is that independent of these events, or is it possible essentially to suppress one of the event and then look at what is the exponent that you get?
Okay, I have one then. So have you tried using the last part of the talk in which you try to change the focal plane? So that will be useful in confocal scanning, in which you don't have to move an objective back and forth. Sure, is there any way in which you could scan different layers?
So you can scan different layers, that's not a problem. But we have never tried pushing it into a microscope and then doing something. No, that was not that.
No further. Oh, yeah.
Stresses, not the oil, but let's say some micellar system or gel, which will also have viscoelastic stresses. So, have people looked at this phenomena droplet in those systems?
I don't think people have looked at this system at all. I mean, there are very few experiments on looking at the turbulence aspect of it.
Not that.
So, no. We did it with the Newtonian fluids. Both the fluids are Newton. But if you add viscoelastic system, and if they have interesting flow properties,
Yeah.
that would again couple to it. So, you already have, yeah. So, I have no answer for it. I don't think that it's
is a spectrum you obtained. The horizontal axis is frequency omega or wave number. Okay.
Okay, so two things. If you did the PIV with, with caution, then that's wave number that you get, a wave vector that you get. Otherwise, it's frequency, and I don't know if I should use the linear dispersion relationship to convert frequency.
Slope is minus 1.4.
And
Slope.
is minus 1.4.
It's the same as a Rayleigh-Benard turbulence.
That's similar as the Rayleigh-Benard.
Bolgian scaling.
Yeah, that's exactly the same thing. But it's surprising that it has that scale, because that has one particular kind of injection of energy. This has over multiple scales. Yeah, you're right.